We did earlier missions to understand some of the atmospheric studies and ionospheric studies, etc. But then a large-scale investment happened with Chandrayaan-1. Today we talk about Chandrayaan-3, the successful landing on the moon, something which we can be very proud of, having the first nation ever to land on the moon on the southern half of the moon. But then I would like to look at how exploration is important for us, in contrast to the other work of space, which is the communication, Earth observation, navigation, strategic observation, and many other applications that we are doing. Because it has a potential to spur new developments, new technologies, and inspiration element, and possibly an economic activity at a later point in time, because it adds value of knowledge, space technology and science to the young people. Because we want you to come and work in this space technology, that inspiration element, I think it is not going to be, a scaling of activity is not going to take place. And this is well understood, and I would like to speak a bit about that aspect. Of course, last year we had 3 important missions, the Chandrayaan-3, not last year, last few years. Chandrayaan-3, the landing on the moon happened. The Aditya L1, the mission of studying sun and launching it to the Lagrangian point happened, and also the EXPOSAT, the study of black holes and its various processes. So these 3 missions indicate the renewed interest and work that we are doing in space to look at exploration as a new agenda. But the very important point for all of you is to understand what are the outcome out of it. I think this is very important. Toward the end, I will stress on that aspect of how we can increase the outcome from these missions. The Chandrayaan-1 gave a lot of understanding which is not existing at that point in time, even for those nations who have done earlier missions to moon. For example, moon is bone dry, moon is geologically dead millions ago, moon regolith completely absorbs impinging solar wind portions, lunar wake is devoid of solar influence, and many others. And we have answers to that from Chandrayaan-1 mission. And this is a global understanding that has come out of Chandrayaan-1. We also made a first impact on the moon. The moon impact probe impacted on the moon and made initial signatures of presence of water on the moon, though it was not confirmed at that point in time. But then Chandrayaan-2 brought new understanding that moon is not that dry, it still has got water on the moon. And today we have mapping of the moon which shows that there is a lot of water on the moon. And this is a great study, and later missions of Chandrayaan-2 also indicated the presence of water on the moon by instruments of India as well as US, other nations also. So there is a greater renewed interest on the moon primarily because of this finding that came out of our moon missions. Again, there are many other findings that came out of moon missions, like the sodium distribution on moon, which was a theory and a scientific discussion which happened, and today we have great evidence of this, which shows the origin of the moon, whether it is from Earth or from any other planetary activities, and some of these findings come out of such critical understanding. I'm not going into the details of each of them. The best of the maps that we have today came out of the moon mission that we did. The Chandrayaan-2 has the best ever maps that we have for moon, the highest resolution map that we ever produced. So sharpest images of Chandrayaan-2 are being used by other nations today to plan their missions to the moon. It's something that we should all be proud of. Of course, we did a lot of studies on the boulder distribution on the moon. For example, the right landing site identification is a very important issue. So when you take a 2-dimensional map of any surface, you can identify a valley versus a boulder. So we need to understand this through 3-dimensional imaging and multiple images. So we have one of the best maps today which identifies the boulder distribution. And this map is so important for identifying landing sites. Possibly when you want to colonize and land on the moon, this information becomes very important. One of the important findings that came out of Chandrayaan-2 is a subsurface features, some craters. So when you look at the images, you will not understand the real crater, and this can be found only by radar imaging of the moon. Today we have even that quality of images on the moon which identifies the most potential craters which are later covered by deposits and other impacts that spend soil on that and are covered in a manner. So it's a loose sand, not a real rigid surface which will appear to be. So this type of even findings which are very critical for landing sites also we have today about the moon. Another real observation about moon is the exospheric argon distribution. Now, moon is not having an atmosphere like many other planets. Possibly it has a gravity to keep little bit of atmosphere, but it didn't stay there. We also know about Mars, which has got a very thin atmosphere. though it has a gravity which is sufficiently high enough to retain an atmosphere. So what processes are happening there which makes this atmosphere to vanish? It's a geological process or it's an extra geological process that makes this atmosphere vanish. And this understanding and scientific research happen to look at some of the trace elements are being mapped to find out what are the transport phenomena happening in the atmosphere and looking at the magnetic activity, etc. to understand this. And this is very important finding from that context. Similarly, Chandrayaan-2 did even research on sun. For example, solar eruptions were observed by the instrument on board Chandrayaan-2. So this is again really an interesting observation that came out of the moon mission. We also did in Chandrayaan-3, there were 5 instruments and all of them worked very well, and many of the publications have slowly started coming, very impactful publications. And one of them, some of the information came out of Chandrayaan-3 I would like to share with you. The surface elemental composition, we had a spectroscopic 2 instruments on board, one based on alpha particle enrichment, another based on laser ablation, and both gave very good output in terms of the surface elemental composition of moon. And this is again a great finding. Similarly, buried craters on the moon. This is again a finding from Chandrayaan-3, which shows that the surface, though appeared as the crater, you won't be able to find out from normal optical camera. We need to look at it from a different set of camera systems which identified the presence of buried craters. It also goes with the evolution of the moon and its surface. Again, elemental composition from another instrument. It's a laser ablating instrument which showed the distribution of elements. And you will ask me why this information is important. And this information correlates with respect to the origin of the moon and how the surface of the moon is changing over time. So there is another interesting finding. The top surface of the moon is continuously being replenished by the material that is coming from underneath and then going on top of it using different processes. Another interesting finding that we got is the moon quakes. That we brought an instrument on the surface of the moon, actually measured the moon quakes, and we have data from that. And some of them are natural, some of them are events that are like something comes and hits, that you have a shock which can be measured. So people are analyzing it, and possibly good publications will come out of it. This is another measurement of the lunar regolith thermal characteristics. So we drilled a probe into the surface and measured conductivity of the surface, which showed that the surface has a very high thermal resistivity. It doesn't actually, heat transfer doesn't take place as much as we thought earlier. So this is something which will be useful to model the thermal behavior of moon later. Similarly, there are other measurements on the surface and ionization, which is done by one of the, it's automatically shifting. Okay, by the atmospheric Langmuir probe. Okay, look at the another data which comes out of the Mars mission. A very lot of findings have come out of the Mangalyaan mission. You call it MOM mission, which worked for almost 8 years, though it was launched for 1 year. We have huge amount of information on Mars today. One of the best maps of 3-dimensional maps of the Mars was made by MOM only. The Astrosat, of course, you know this Astrosat is one of the observational platforms that we launched, similar to though they are not in size and complexity as big as the Hubble, but Astrosat is one of the first ever satellite that was launched, which has a multi-spectral capability. And a lot of science has come out of it in terms of the processes that are happening in the universe, in terms of nebulas or in terms of collisions, in terms of explosion of stars. I think they have been observed quite a deal, and a lot of publication. One of the best ever publication has come out of Astrosat science. Of course, a few of them which I would like to share are the Crab pulsar observations from the Astrosat. Then some of the gamma ray bursts that it has detected in the universe, especially in the quiet stones. The name is mentioned as, sorry, I'm not able to come to this mic, it echoes, of Stephen's points showing features of which were never seen in the past. Let me quickly shift to another satellite, which is the Aditya L1, which was launched recently, and it captured one of the best ever solar eruptions. I think this was the solar maxima period, and the highest ever eruptions happened is this year, and we have huge amount of observations and data collected on the processes that are happening in coronal mass ejections, has impact on the space weather. And Aditya L1 is equipped with the 7 instruments, some of them measuring the particles, some of them measuring the X-rays in low energy and high energy, some of them looking at the magnetic effects. I think all of these combined observations are going to give you a huge amount of data on the process, linking the CME to the space weather effects, especially dealing with the, you know that it has an impact on the client communication, the external magnetic field, the particle distribution around it, and also how it disrupts the communication networks as well as power distribution networks. So this information are gathered today. Of course, some of the publications are slowly coming. All of these observations happened just this year. This is another observation from the yet another instrument on board Aditya L1 called the solar coronagraph, which looks at create an artificial solar eclipse and look at the corona. And the yet another instrument is an ultraviolet instrument which looks at the sun in an ultraviolet spectrum. So I'm just showing some of the data. This is a full disk image of the sun observed in various spectra by the suite instrument on board Aditya L1. Now why I said all of this is, though we did all these science missions in the recent times, it has produced significant science outcome. And I would like to speak about that part a little later and how you can increase the impact of what our missions that we have done in the recent times and in the future. Before I go further, I would like to tell you that recently that a space vision has been announced by government with a goal of expanding the exploration and other related activities in the Amrit Kal, leading up to a landing of a human being on moon by 2040. So this involves expanding our Chandrayaan program, looking at other planetary missions, building up a Bharati Antariksha station, creating heavier launcher capability, and all of these are part of this. And for that, there is a huge amount of investment also identified at this point in time. So basically, the goal of this announcement is to expand the Indian space flight program. Though we have been operating at a certain scale in space, primarily looking at the communication, remote sensing, navigation, and other areas in lower scale. So our current number of satellites are hardly 50-55 numbers. For a nation like us, I think we need to have hundreds of satellites, possibly maybe much more, to handle tasks related to frequency of imaging, looking at disaster warning, resource mapping, giving communication direct to devices. I think all of this demands huge amount of investment and infrastructure. To scale up this space activity to a next level, possibly a 10-order increase in the economics, I think we need to do a lot of things, especially bringing private entrepreneurs into space ecosystem, providing a conducive environment for them to do all of that. And also we need inspirational programs like the one which I am talking about, the human space flight program and science program, where we want scientists to come and participate and create a very innovative ecosystem. So this is precisely the goal of the Space Vision 2047. And we have looked at this Space Vision 2047 in 3 segments. What we can do in the near time, something like 5 to 10 years, and then long time by 2040. The first part of it has already been approved by the government and funded already, building the newer launcher capability, the first module of the space station building, at least 2 missions to Moon, 1 mission to Venus, building the first part of the Bharati Antariksha station, and also expanding our human spaceflight program. The space station is one of the important elements in this exploration. We would like to look at a permanent station where Indians can go and work in microgravity environment and conduct research. I think the first part of it is going to be built and launched by 2028 and fully completed by 2035, where human beings can go regularly and operate. And we look at many activities around this space station, and currently we are in discussion with many stakeholders, especially national laboratories, research institutions who are interested in science research, etc. One of the important topics which I would like to discuss is engagement with the stakeholders. In a time where we are discussing this topic with INSA, I think a lot of researchers are also here. We are looking at many of the science programs yielding a lot of research, but the publications that are coming out takes long time. It's primarily because our pool of researchers available to do this, converting the knowledge, information that we are getting into research outcome is actually low. We conduct these programs regularly in terms of data utilization programs, combined research, etc. But still, this is not growing. If you really look at, many institutions are part of our work. It's not on the ISRO alone. The science data that comes out of these missions are actually available in a public place, and all of you can download and use this data and create value out of it. So basically, we would like to look at how we can expand this science data utilization and create more astronomers and space researchers out of this. So we would like to work on this engagement and also look at a long-term plan of exploration in a manner which will be suitable to you, suitable to the interest, and suitable to the knowledge that is required. So this is the primary goal, and we have a lot of programs, and some of them are the institutional programs. We deal with the other ministries, department like Department of Atomic Energy, the IIG. We signed with MOUs, the MGRI, and many other institutions. Primarily look at how we can collaborate and work on future exploration missions. Similarly, is the interest with the student community. We have a program coming up called START program, bringing students to work with us in terms of future exploration science research. And these statements and announcements soon come, and I invite all of you to be part of it. And we also have national space science meetings, symposium meetings, where we look at brainstorming and workshops to identify what all new science programs are required for the country. So out of this, we have created a roadmap for the next 25 years or so, which are the new science missions and programs that we need to plan and work. I think it requires maybe 5 to 10 years even for planning. What are the type of instruments that we need to work on, which are labs that we can really collaborate, what science outcomes are necessary, how much funding it is needed, and what capability we need to do research a priori before we commit on a program. So I use this platform to announce that it is our interest and this nation's interest that we should work on explorations in a big manner, because it has a multiplier effect, especially with regard to the technologies that will feed into our operational programs, the autonomies and other advanced technologies that will go into the systems that we are working on, and of course creating a strong pool of talents who will work on this for a long period of time to create new knowledge that is needed for the humanity. Let me thank you and wish all the very best to Future Science Exploration Program, and thank you for giving me this opportunity.
Thank you, sir. I now request Professor Ashutosh Sharma, President of INSA, to formally induct Dr. S. Somnath with the scroll and Angavastra. Thank you, sir. I now kindly invite